Again, the exam is going to be 24 questions. You're going to have 1 hour to do it, which might seem like enough time since this is open note, but I promise you almost everyone took the whole time last semester. You can go to either section, open internet, open note as usual. I would solve all the multiple choice questions first. They're worth the same amount as free response. And they're going to be about 50-50 proportionally. Don't use ChatGPT. It'll literally give you all the wrong answers, I promise. And last semester's average was 80%. And I believe, and all of you guys are doing great. Okay. So I think these are all of our participants. You guys can join at any time. All right. So my first question to you guys is, what factors affect how a band of the same size would be seen on a gel? Like if you run your electrophoresis, what are some factors that can influence how far your DNA will travel? Okay, awesome. So that voltage, whether you use a high voltage or a low voltage, will influence how quickly that DNA can travel. If we have really high voltage, it'll travel faster. That does generate heat, but temperature isn't really a factor that influences how DNA will travel, just in the electrophoresis technique alone, right? The agarose percentage, definitely, and we'll touch on that in the next question. In time, of course, if you let it run longer, it's gonna, the DNA will travel further. Let me know if there's any questions on that. Otherwise, I have an image that goes with this. So first, you have two researchers running the same DNA fragment, 2 kb, and they use the same voltage, same runtime, but the percent of agarose is different. Okay, so here are the 2 gels. Okay, so you're going to have researcher A on the left here and researcher B. And it's the same fragment, but they've traveled different distances. And my question is, which one has the higher percentage of agarose in their gel? Okay, almost everyone's in there. I'm going to go ahead. Exactly. Okay, awesome. We don't need to really talk about it then. You guys got this, that if there's a higher percentage of agarose, it's going to be a thicker sieve for the DNA to swim through, and it's going to get stuck higher at the top, whereas this is a lower percentage. Perfect. Okay. So this is kind of a similar question, but which gel has a better resolution of that 2 kb band? Here's that gel again. Okay. Okay. All right. So what do I mean by resolution? Resolution kind of means like focusing in on your bands better, making it clearer. And what that means in terms of like the gels is kind of like in relation to the ladder. Like if we have a really thick, if we have a band and it's really condensed, we can't really resolve like where it is in accordance to the ladder. You know what I mean? Like maybe the ladder has all of its fragments squished. It's a little bit more squished here. We can't really tell, like, does it look like it's 3 kb, 2 kb? The bands will be kind of squished together. The ladder will be squished. So we won't really be able to tell. We can increase the resolution by decreasing that percentage for, it depends on the band size, right? If you have a larger band, which 2 kb is pretty big, then decreasing the percentage of agarose is going to allow you to spread out those larger bands of the ladder, larger sizes, right? And so, this is like 3 kb, 2 kb. Now we can clearly see, where our band is. And if this is a 2 kb band, it should be a little bit closer to there. But this kind of increases our resolution. Does that kind of make sense? So he said a higher concentration had a better resolution, but it depends on the size of your DNA. If you want to increase the resolution of a very, very, very tiny fragment, then that's exactly what you want to do. You want to have a higher concentration. Okay. Does that make sense? I can clarify that further. You guys let me know in the chat if you want me to clarify that. Or are you guys good? Makes sense? Okay. Yeah, so smaller bands needs a thicker concentration of agarose to resolve, whereas a larger band needs a lower concentration of agarose. Okay, so our next question is, we have, and there's an image here too, we have 4 researchers performing independent PCR reactions, okay? 4 different people doing 4 different PCR reactions, but their goal is to get the same amplicon, the same fragment amplified. That's 1 kb long. Only the 4th one was successful, and we're going to start with number 1 over here. So looking at what happened to number 1. So I forgot what my options were here. Adding too much primer. Was the melting or annealing, like aka the annealing temperature of the PCR too low, too high? Did we forget a component of the PCR reaction for researcher 1 here? We have multiple bands going on here. We were only supposed to get 1, right? So researcher 1 or researcher 4 here was able to get that, nice band at 1 kb. Okay, we have pretty much everyone in here. I'm going to go ahead. Okay, perfect. Well, let's make sure everyone's on the same page. So adding too much primer is not going to cause this, and we'll get to that in a minute, but the annealing and melting temperature is really what's going on here. So if you manipulate the different temperatures of the PCR reaction, different things will happen. For example, the melting, aka the annealing temperature, is meant to get those primers to reanneal onto the DNA fragments or the amplicons. And if that is too high, what happens? If the melting temperature is too high, what happens? In this case, it was too low, but what would happen if the annealing temperature was too hot? Exactly, nothing attaches. Our hydrogen bonds are not going to be stable enough to the DNA, and so it won't attach. We typically want it to be around 55 or something, 56 or something. If they're too low, then we get these multiple bands. Why is that again? What do you guys think? Why do we get multiple bands?
Isn't it
Not exactly. We're not really touching the denaturation.
binding?
So yes, David, why are we getting all the random attachments, at a low temperature? So non-specific binding. Why is that happening? It's not too important, but it would basically be because the hydrogen bonds are stable enough to be non-specific, because it's at a colder temperature, and so it forms those non-specific bonds at different regions, amplifying different random pieces of DNA that were not what we were looking for. Okay, now the next question is looking at researcher 2. Okay, so I'm going to move on over here. So what happened to the second PCR reaction? We have, maybe a small band over here, which, should be our fragment of interest, but we have a lot of bands, maybe a fuzzy band that's pretty small. Okay, I got almost everyone in here. Okay, good. So we added too much primer, and I accidentally did this for the morning section one time. I added 10 times more primer than we needed, and you guys ended up with a bunch of primer dimers. So if you have your concentration of primers way too high, then those are just going to find a way to attach to each other, not perfectly, but they're just going to attach to each other, and you might get something like this. So your reaction will not be efficient. Okay, hopefully that makes sense. Okay. Next question, just looking at researcher 3, what happened here? So all of our DNA is at the top. Actually, I'm going to consider the annealing temperature too high, possibly right. Yeah, that could possibly be right. My bad. If it was too high, then the reaction wouldn't have worked, but you still might end up with all the DNA that you started with, which would still be the same case as if you forgot a primer or polymerase in your reaction. So I'll consider both of them right. Okay. So that's good. Any other questions? Which one of these enzymes is necessary for, let's say, gram-positive DNA extraction? Try to remember the differences that we had between, if you remember that chart I made, talking about the differences between plasmid DNA extraction, genomic DNA extraction, gram-negative, gram-positive. I'll give you guys a couple seconds. Okay. All right, next question. Which of these elements are necessary near the multiple cloning site for our plasmid and our reaction? The multiple cloning site region. Okay, good. We need our ribosome binding site to start expression. We need our thrombin cleavage site because that his tag we want to cut off later, and that's what the thrombin site is for. We need our T7 promoter and terminator and our lac operator, which will help control the expression later on. But you don't need to know the in depth about the his tag lac operator thrombin site yet. That's for later. Just know that it exists and it's near the multiple cloning site. Okay. And this over here is the image that you can reference. Okay. So definitely be comfortable with this. It's in one of the slides. Okay. All right, so there's another image associated with this one, but we have 3 researchers performing restriction digests on a plasmid. And so which one did researcher 1 use? Okay. So here we have restriction enzymes A, B, C, D, E. Okay. And notice that a couple of them replicate or the sites are found in multiple places on the plasmid. So we're just looking at the first well over here, the first column. And these are the bands that researcher 1 got. Okay. So you might need a little bit of time to calculate this, but go ahead and see if you can figure out which which restriction enzymes were used in the first column. If you're not sure what to do exactly, that's okay. We can walk through it. Okay. So The answer is A and D. Okay, so how did I get those restriction enzymes? All right, the first thing you need to notice is that we have 3 bands here, okay, which means it's been cut 3 times. And so that could be from many things, but you want to hone in on these values. So we have here 1,800. Okay, and let me give me a highlighter over here. Try to basically calculate the distance between every single one of these pieces. Okay, that's the first thing I would do, is calculate every single distance between each piece. And that'll help figure out what could be, that's the first step I would take. So this is 1,800. So that 1,800 would be the distance between both of the A cuts. And then you can continue to find any patterns here. You'll find that the distance between D and A over here is going to be 2,600, because this 11,700 will be subtracted from the total 12,000 base pairs. Okay. There's 300 here and an additional 2,300 in this segment right here, leading to 2,600. And then you'll have a fragment like 7,600, which will be the remainder of the fragment here. Okay. Another approach I usually take with restriction enzyme problems is like just testing them out. I just try like random combinations and see like what could it be. Here again, we have 3 bands, so we're going to need 3 cuts. So that could either be with like A again, it could be with C, it could be with, you know, B, E, D. So whatever combinations, I would try them out. For example, like it's probably not going to be both E and B because we don't really have a band that small, right? So kind of narrowing it down like a puzzle, like logic, is kind of like the fastest way of doing it. Okay, okay, you guys are doing better. This is good. Let's see if I can have my iPad. The first thing I would have done is to go ahead and identify what are the lengths between each of the cuts. We see that there's a band that's 4,400, just like in our gel over here, our second band is 4,400. So we're suspecting that we're going to have C and E. Okay, just to double check, we're going to go ahead and measure the bands between C and E, sorry, C and C over here. So if you add up this portion, this portion, this portion, this portion, you should get like 4,900. Okay. And then we're also going to have another band from back to C over here all the way to E. And that's going to be 600 plus 1,800 plus 300. Okay. And that's going to give you that 2,700. Okay. So does that make sense? That kind of thought process? Is there anyone who might need, I can go through this more carefully after as well. But does it make sense for now? Yeah. Okay, awesome. I'll let you guys try the last one. Okay, most of you guys are in. Okay, pretty good. Pretty good. So it's going to be B, D, and E. So the first thing you should see is that we have a really small band of 300, which matches this really small region fragment right there. So you are automatically thinking, okay, probably we're going to be using E and B, and then maybe one more. Okay, so we have a fragment of 5,500. You're going to go ahead and look to see, how you can get that fragment. If you just go this way, you'll see that 4,400 plus 1,000, or sorry, 4,400 plus, supposed to be, sorry, there's a 0 missing there. So, yeah, 1,100, then that's going to equal 5,500. Okay, so that should also help you conclude that D is involved as well, because you're going from E to B, from E to D, which is that 5,500. And then if you want to confirm that, you can calculate how much this long fragment is all around here, and should be 6,200. Okay. So it's basically just cutting around, figuring out how long all the fragments are and where the pieces fit. Okay. Okay. So if you guys have gotten this question a lot in your practice quiz, if you've looked at it already in the practice exam. So if you have a region here, and let's imagine, there's a whole plasmid, and you have your target DNA, you're trying to figure out, was our gene of interest inserted correctly? Okay, so we've gone through this before. How could we confirm? How could we validate that our fragment has inserted specifically our fragment of interest and also inserted in the right orientation, using these potential restriction enzymes A, B, or C? Okay, and we have those repeats there. In the green is where that DNA target, where this DNA fragment would be here. That's how long it is. Okay, and you can pick. Okay, awesome. Okay, I'm glad this is controversial. So B versus A. Okay. If we were to use B, okay, what would be distinguishable? What could distinguish a reversed insertion versus a correct insertion? We wouldn't be able to tell because it cuts from the beginning of the fragment to the end of the fragment, which would be the exact same situation if it were reversed. Because restriction enzymes can function like palindromically, right? It recognizes palindromic sequences. Even if we reverse that DNA target, those sites will be in the exact same spot. It'll be flipped, but like the sites will be in the same, basically the same location again. And so that won't really tell us any other information. It'll tell us that there's going to be a sequence that's around, what is this, 1,500 plus 5,500, so it'll be like 7,000 base pairs long, but not much more than that. A, however, will tell us with specificity which direction it inserted in, because here it gives us a fragment. Okay, so if we cut with A, we're going to get a specific fragment, 2,500 base pairs long. But if it inserted incorrectly, we're going to get a different size fragment, right? So that'll help us distinguish. Specifically, because we have in a restriction enzyme site on the outside and on the inside. However, if A was straight up in the middle, this could be a problem, okay? Because if restriction site A, this one was moved straight in the middle of our DNA target, then if it were flipped, it would stay right in the middle again, right? So it's important that this is, unbalanced. Hopefully that makes sense. Let me know if you guys have any other questions on that. My next question is regarding like how long would these bands be? So how long would it be if it were correctly inserted versus incorrectly inserted using A as our restriction enzyme? Okay. So this is a little bit tricky, but notice that this plasmid is, roughly, let's say 10 kb long, okay? And this piece pops right out, okay, great. What's keeping these sticky ends from reannealing, right? Nothing. So we could end with a band in our gel that's 10 kb long, which is just our fragment. Even if it didn't anneal, actually, we would get a fragment 10 kb long because our plasma didn't go anywhere, right? So important to keep that in mind, right? We don't want to be surprised when we see a 10 kb fragment. If it were incorrectly inserted, then imagine this flipped. I actually have it drawn here. If the DNA target were flipped, then our A would show up over here, okay? And so, sorry. Then we would have from A to A, it would be 1,000 plus 5,500, 6,500 total. We would still get that 10 kb fragment as well. Hopefully that makes sense. That's why we end up with 2,500 and 10 kb if correct, and 6,500 and 10 kb if incorrectly inserted. Let me know if you guys have any questions. Did you explain again the 6,500? Yeah. So if it were incorrectly inserted, our DNA target like is still in like the same spot. It's just inversed, which means that the site that was within it, the restriction site A that was within the gene, is now on the other side, right? Because over here, A was on the kind of like the left side. Now it's over here on the right side. And so we have to consider this fragment, which is a different size than this fragment, right? Because we're cutting both A's, A to A. We need to consider that distance. Does that make sense now? Okay, awesome. This is kind of like the last question. So this is about like the primer combinations. Okay. So, sorry. My question is, which primer combination will tell us if our fragment was inserted correctly? Okay, so you can choose between A through E, I mean F. And there's a few of them that are correct. You guys can put them in. Okay. Not bad. Okay. The key is when in doubt, always pick a primer in the middle. Okay. So here I've highlighted only the correct ones. I excluded all the incorrect ones. So like A, and D are not going to be useful to us. Because we need a primer that either touches like within like B or is literally inside of our target gene. So we can really validate that our primer is amplifying our gene of interest. These are the different links that you would get. So if you were trying to run this on a gel, all you need to do is, connect the different primers to see how long your band would be. But imagine that if you're didn't insert correctly in the right orientation, then you wouldn't get any bands at all because the primers would be wouldn't have like their matching pairs. But yeah, so again, the key is picking primers that are within primer pairs that are within the gene. Does that kind of make sense? It's kind of like all you need to know about that.